Uh, Welcome everyone. This is Upmanu Lal from Columbia University. Actually, I'm getting an echo. Let me just stop that. So on behalf of our project and Quasi, I would like to welcome everyone to today's talk, which is the very first in a series. And to start it off, we have a very appropriate speaker for this series, which is Dr. Vincent Tidwell. And as you probably saw from his bio that was posted, he's at Sandia and is a distinguished member of their technical staff. But more importantly, he's been the leader of looking at water energy interactions and developing a comprehensive understanding and mapping of the interdependence between these two things, and from a hydrology point of view, a comprehensive mapping of water resource use across the country. It's really fascinating work that he's doing, and he's a key partner in our project on America's Water, and we are looking forward to listening to him as well. We have a website that's being put together where we will have publications and presentations from different groups that relate to this topic. And if you have things you would like us to feature there, please do point us to them. That would be much appreciated. So with that, let me get this started, and then maybe at the end, I can talk a bit more about our project and what we hope to accomplish, but I don't want to take up time for doing that. I would rather have Vince talk about the stuff he's doing. So let me turn it over to Vince.
All right, thank you, Manu, and I appreciate the invitation to speak, and I appreciate everyone taking time out of their busy day to join us for this meeting. See when this comes up. The subject that I wanted to talk about this morning is Energy Water Nexus, the past, present, and future, along with to follow the scheme of this webinar series. Do we have the slides up yet? Or do I need to do anything on my end? Looks like all I'm seeing
I
is
think we are trying to figure that out.
Okay.
You're sitting right there.
I know.
So
Let me see.
I think, Vince, do you have a thing which says share my screen?
Yes, I do.
If you click that, then I think you get control.
Okay. Should I do application or Windows?
I think application is fine.
Oh, now it's up.
Since I've got it pulled up, I think you're good to go.
Oh, let's see. Okay, here we go. Now I think I've... Well,
I'm not seeing it.
Well, maybe because I'm... Okay. How are you seeing it now?
No.
Yes.
You are? Okay.
Yes.
Okay. So hopefully everyone else is seeing this. Looks like I'm getting a lot of yeses here, so good. Okay, so many of you probably know something about the Energy Water Nexus. Basically, what the Water Energy Nexus is the fact that we use a lot of water to generate energy. And we use that water for cooling our power plants, emissions control within these power plants, to extract energy minerals, as well as to process the fuels that we use. So water touches energy in many different places. Also, from the water sector side, we use a lot of energy. We use energy to pump water, to convey, treat, distribute, and to condition that water for its end use. So let's start with the WaterEnergy Nexus from the past. And as you know, energy is integral to the economy of the United States. Cheap energy has largely fueled our economy, and over the years, the evolution of the energy sources that we use have changed, starting with wood back in the mid-19th century and moving to coal and petroleum. I'm having a lot of feedback now. And how some of that, the evolution of that energy use has both been marked by changes in technology and has been driven to some extent by changes in technology. But an important part of all of this is recognizing that most of these energy sources in one way or the other are pretty water intensive. Coal, natural gas, petroleum, even nuclear electric power, all of these use water in some sense and are for the most part quite water intensive. Even our renewable energy sources tend to use a lot of water. Hydroelectric power, biofuels, even some of our solar thermal processes use a lot of water. So in terms of hydropower, you can see the ramp up here from the 1950s to the mid-70s, a lot of capacity added to our system. Now we use about 6 to 7% on average of our total nation's electricity demand is met by hydropower. But here after the mid-70s, you can see quite a bit of variability in time. This is not because the capacity has been changing over time, but simply variations in climate have driven these changes in hydropower production, among other things, but largely driven by climate. And so you can see here a very strong signal, energy-water nexus signal in the hydropower signal. Also here is data from the USGS starting back in 1950 out through 2010. You can see the different water sectors, water use sectors, irrigation, this kind of greenish color, and more specifically interested in the thermoelectric here in the gold. These are withdrawals, and you can see how withdrawal has really grown over the past, well, from 1950 to roughly 1980. Here again, largely driven by rural electrification, expansion of our economy, industrialization. But then after this, and I guess the important thing to note here is that after 1965, it was the largest user of water in the United States and continues to be so all the way to 2010. Now this is all water, not just fresh water, but even if we had fresh water here, it is the largest user of fresh water as well in the United States. We also have a bit of energy or water use here in this other sector, which would be the water for extraction and processing of fuels. The other important thing to note here, though, is that after the 1980s, things tend to level off, and you kind of question why this would be the case because, our demand for electricity has continued to grow. Well, actually, this is driven by largely the cooling systems that we use in our power plants. Historically, we've depended pretty heavily on what you call open loop systems or once through cooling systems, which basically just diverts the river, runs it through the condenser to cool the steam down into liquid water, and then all of that water is then returned to the stream or river from whence it came. So we have very large amounts of water being withdrawn, but most and all of that really returned back to its where it was taken from, with some level of evaporation then lost due to the heating of the water that's returned. The other style of cooling system, which is the closed loop system, that's where basically we take the water from an aquifer or a river, but most of that, really none of that water is ever returned. It is then used through a cooling cycle, through evaporative cooling, then is used to turn the steam into liquid water. So in this case, we're withdrawing much lower quantities of water, but all of that water that is being withdrawn is largely lost then through evaporative loss, or then is consumed. So the story here is that after the 1980s, most all new power plants were equipped with the closed loop system. So withdrawals then, pretty much tapered off or leveled off over time. And so that's the reason that you see that kind of leveling off in overall water withdrawals in the U.S. It's not because we're not building more power plants. So then, you can see that, even today, water use practices for proposed new energy conversion facilities, so for new power plants, we're seeing more and more controversy, more and more difficulty in being able to get water for these. And so, we're anticipating that the frequency and bitterness of these conflicts will increase. But you can see that this statement was made back in 1980. It's from a report from 1980. So this water nexus issue has been around for a while. People have been concerned, have been kind of watching it. I think now is the time when we're really starting to see the incident of these conflicts and issues really coming to a head, that it's now time that we have to start taking some actions with these. So what is the energy water nexus today? What does it look like? What does that footprint look like? So let's break this down into several different categories. Let's first look at water use for cooling thermoelectric power plants and in emissions control. And as I've already mentioned, thermoelectric power in terms of withdrawals are the largest user of water in the United States. This is just freshwater use. You can see that it's pretty comparable to agriculture now in 2010 in terms of total withdrawals. The picture's very different in terms of consumptive use. As you know, since 95 was the last time the USGS did a comprehensive analysis of consumptive water use. They have recently done an analysis of consumptive use in thermoelectric power. It's on the order of about 4.5 billion gallons per day. So still, again, in this 3, 4, 5% total consumptive use area. So it's much smaller than agriculture or even municipal. So you might say if thermoelectric consumptive use, which is usually what we worry about, it's that amount of water which is taken out of a river or aquifer and not returned. It's evaporated or incorporated into products or whatnot. So that's the water that's not available downstream for other uses. So that's what we usually worry about. And here you can see if it's such a small part of the pie, why do we worry about it? Well, it's because it's this small part of the pie, the municipal, industrial, thermoelectric. That's really where the growth is occurring these days. Agriculture's been, in terms of consumptive use, has been relatively flat over the last 20, 30, 40 years. Thermoelectric, municipal are where the real opportunities for growth are, and that's why this water energy nexus is important here with respect to thermoelectric cooling of our thermoelectric power plants. Here it is mapped out all over the United States. This is work done by the concerned scientist. Kristen Averitt in particular was the lead on this work, but you can see the different size symbols represent how much water is being withdrawn for these different power plants. You can see that most of the big circles are blue, have to do with the open loop cooling. Most of these are in the east where their water is much more plentiful, or along the coast here in California. So you can see that power use is distributed all over the U.S. So those large statistics, while they tell us something important, the really important part is place really matters. It's where this water is being used that ultimately matters. And so to really understand how important that water use is by thermoelectric power is how does it, line up with other water uses. So here you can see, a very different pattern of water use than we saw before with the thermoelectric. Here, much of the water use, and this is in terms of consumptive use, is occurring in the western U.S. due to agricultural irrigation, and along the Mississippi Valley, a little bit in Florida. We also have to put that in context with groundwater recharge, stream flows as well. These are the supplies of water where it's lighter colored. That's where, recharge and stream flow are less. If we put all this together, it helps us to understand, and there are many different ways of constructing these metrics of limited water availability, but here you can see the top ones for surface water. It's basically where current consumptive use is on the order 70% or more of the annual average low flow stream flow in those areas. So you can see that much of the West suffers from, fairly limited water in these areas. Also, the lower map shows where limited groundwater availability, where the pumping is on or exceeds the sustainable recharge level. So, and these go along with our intuition about where water is limited. So when we start looking here, you can see that, again, why many of the open loop power plants are located in the east, where water is a bit more plentiful, and we're not consuming as much of it because we're not doing as much irrigation. Whereas we've got a bunch of power plants which are tend to be recirculating, which tend to consume more water, located out here in the west in areas where we have limited water supply. So that's again, its place really matters in understanding where these plants are relative to other water issues, and we'll talk some more about that in a moment. We also have to be concerned about the amount of water that's used for energy extraction and fuel processing. And so in a recent study by the Department of Energy, they determined that about 2.5 or so billion gallons per day, in addition to that water that's being consumed for thermoelectric power plant cooling, is being consumed in extracting and processing energy materials and fuels. And so all told, about 6 or 7% probably of all water consumption has one way or another to do with the energy sector. But again, place really matters. Where we're really starting to see some growth is in gas and oil shale development. So you can see how these different plays are distributed all over the U.S. and particularly out here in the West, where, again, if you think back to the map that I showed a moment ago, where the limited water supplies are, much of these deposits and plays are in places where water is of limited supply. Another important thing to keep in mind is that, different plays, because of the geologic character of these reservoirs, as well as the way they stimulate and drill and produce the wells, will also vary the amount of water required. So these are some different plays and how much water is involved. But usually, kind of as a rule of thumb, you're looking somewhere between 2 and maybe 10 million gallons per well to drill or to construct and then to stimulate. And in many of these plays, there's well over 1,000 wells that are drilled. So you can imagine that this gets to be a pretty important amount of water. And so here's a snapshot of, at least in the western U.S., where how much water is being consumed for coal, natural gas, and oil extraction. And you can see that much of this, again, is located in these areas where, we have limited water supplies. Just also as a way of kind of pulling all this together in terms of, how much water is used for extracting the minerals relative for cooling the power plants relative to just operating the facilities. And this is some work done by Meldrum and others at NREL a few years ago. Here you can see different types or different systems for generating electricity, all the way from wind and PV down to natural gas and coal. You can see the different color bars, basically this is the life cycle water consumption, so gallons per megawatt hour of electricity generated. And so the blue is the power plant water used to operate just the facility itself. The red is for extracting and processing the fuels that drive those facilities. And then the green is the amount of water that's used to cool the steam cycle. And so you can see that overall for, in all cases, it's that the cooling cycle that consumes by far the most water. But nevertheless, the fuel cycle can be pretty important, particularly for nuclear and coal. The natural gas, even though, a lot of water is used in stimulation, in generating the wells, a lot of gas is generated. So in terms, in a life cycle calculation, the amount of water that's actually used in the minerals processing and extraction is pretty small relative to the cooling cycle. So now what about the other side of the coin, the water used or the energy used in producing water for pumping, conveying, treating, and distributing, etc. And so this is some work that we recently did focused on the western United States. We're in the process now of extending this into the eastern U.S., but we mapped out on a county level how much electricity, so this is just for electricity, is used for different water services. So large-scale conveyance up here in the upper left, how much electricity is used to pump groundwater for agricultural purposes, to pump surface water for agricultural purposes, and then down here on the bottom for drinking water, this is both the amount of energy to lift the water if necessary, to convey it, to treat it, and then to distribute it. And same here for municipal wastewater. And so you can see that each one kind of has a different footprint in terms of where the electricity use is most, has to do with the depth of water, has to do with the kinds of treatment systems they're looking at, et cetera, and how it all rolls up. And you can see that, in particular here in the far southwest, largely because of some of these large conveyance systems like the Central Arizona project, also because of a lot of groundwater pumping here in the Central Valley, et cetera, you can see that every county in the western U.S. uses some electricity for providing water services, and on average, about 6% of all the electricity use in the West goes to providing these 5 different water services. A study by Kelly Sanders while she was at UT found that 12% of all energy use, so not just electricity, but all energy use goes to the water sector, but that also included end use, which I don't include here. So bottom line is, the use of electricity and energy in the water sector is very important. So now let's pull all this together. And here you can see in this upper graph, we've pulled all the water use for energy, so power plant cooling, energy extraction, processing, biofuels at a state level. And what you can see is kind of a regional pattern form here. You can kind of see the footprint of the biofuels in the Midwest. A large part in the east here is largely due to large withdrawals for thermoelectric power plants. You can see kind of a very different pattern when we start talking about energy use for water services. So again, for conveyance, groundwater pumping, drinking water, wastewater. So a lot of this is out west, largely driven by a lot of the irrigated agriculture out west and some of the major conveyance projects. But the point here is that we have, this water energy nexus occurring over the entire U.S., but that its complexion, if you will, changes as we look at different places. This is a regional issue. Different issues come up in different parts of the United States. However, all see one issue or another of the energy-water nexus. This is another study that was done fairly recently by the Department of Energy. And what it shows is that we're already seeing impacts between water, climate, and energy. And these are just cases, each of these icons are cases where there has been some kind of impact on energy systems between 2006 and 2012. And you can see from all the different symbols, there's really no energy system that's immune for some impact of climate and water on energy production, all the way from damage to systems because of flooding, to power plants that can't operate because there's not enough water or the water's too hot, to wildfires, impacting transmission, hydropower production, even to barges moving up and down the Mississippi. So we have, and this covers the whole United States. There's problems across the entire U.S., and different problems are kind of centered on different parts of the United States. So that's kind of the present condition that we have. Where are we going in the future? And so basically we have a couple of important stressors to the system, like with almost anything else, particularly across the water board. We're worried about growth in population, roughly, just kind of the baseline projection from the Census Bureau, about 27% increase over the next 40 years. On top of that, we have a lot of uncertainty about climate and its variability and how it will affect the availability of water. But on top of that, both the growing population and the potential for changing climate, warming conditions will put greater demands on water across the board, but also will put greater demands on thermoelectric power, for our fuels, even for our water use, which also puts more concern on our energy production. So let's take a look at a few of these. And so there's been a number of studies that looked at, what might be or how might consumptive demands change as we look forward in time. And, among these studies, it can run anywhere from the low 20% increase to upwards of 40 or 50% increase in water demand for thermoelectric power, depending on the kinds of conditions. If there's a lot of carbon capture and sequestration, which tend to be very water intensive. What I've shown here, we looked at several different scenarios, but the point is what we really worry about are where are the power, or what is the potential for new power plant siting in areas with limited water supply. So if you remember those maps I was showing before with the red areas, these are those red basins, and then what the potential for new power plant siting in these areas might be. So about 25% of that new water demand is likely, unless we change things, to occur in these either basins for surface or groundwater where there's very limited supplies of those waters. So again, place really matters about as we think about where we want to site that new power production. Also, another place that's likely to see growth, so not only is our demand growing, not only is climate impacting us, but also the intensity of the water use in generating, in extracting, and in processing the fuels for our liquid fuels for transportation. This is some work by King and Weber from the University of Texas. And here you can see different ways of generating liquid fuels for cars and the amount of water consumed per mile traveled. And it's important to note that this is a logarithmic scale, but here you can see that for gasoline and diesel, it's on the order of 1/10 of a gallon per mile traveled. But as we get down here, as we start looking at things like shale oil and tar sands, we can see that a good 2 to 3 to 4 time increase over conventional gasoline in terms of water use. Electricity, depending again on the kinds of generation, but on average today it's a 2 or 3 time increase or so. As you get down here for biofuels, again 2 or 3 times if they're not irrigated. If they are irrigated, we're looking at what, 100 times or better increase in water consumption. And then algal biofuels much higher. So again, this not only are we facing increased demands, but also the intensity as we move to these other sources of fuels. What about on the water side? We're depending more and more on reuse of municipal wastewater for desalination. Each of these have a much higher use of water or of electricity or energy than the conventional treatments that we use today. So again, this is going to tend, not only are we using more water, which is going to require more electricity, now it's more intensive to use that water because of the increased treatment. We also have increased the potential for the need for increased treatment because of pharmaceuticals and other kinds of chemicals in our drinking water, so pushing higher and higher treatment standards, and that again is going to require more and more electricity for treatment. On top of that, there are a number of pipelines which have been or in the proposal state. Some are even beginning to be constructed in the western United States that will require considerable amounts of electricity or energy to lift water, to move it across basin, between different basins, so achieving interbasin transfers of water. So again, another place where that energy demand may be increasing. So there's a lot of reason to realize that be concerned about increasing demands for water and electricity in this nexus going forward. So what can we do about this? Well, U.S. Department of Energy has been taking some steps. They've recently put together this WaterEnergy Nexus report. It was released in June. You just Google this name and you can find the report there online. Basically, it provides a real nice foundation for the review of this energy-water nexus. What's going on? What are the issues? What are some of the technologies that are coming along that can help address this? So let's talk a little bit about the strategies that they propose. There's 6 strategic pillars that are addressed in this report. The first one is optimizing freshwater efficiency for energy production, electricity generation, and in-use systems. In other words, using less fresh water in our energy production. And so there are a variety of things mentioned there. One, of course, is just improving our cooling systems and new technology that would make better dry cooling or wet cooling systems. And in fact, EPRI and NSF have recently cooperated to develop some new programs to enhance and try to accelerate some of that research around cooling systems. Here's again another figure from the Union of Concerned Scientists, but another opportunity for us here is by just being real considerate of the kinds of power plants that we're building, because power plant water use depends on the fuel type, the cooling type, the emission controls, its age and location. And so here from this graphic, you can see that for different cooling systems along the top, the blue is the amount of water withdrawn, the red is for consumptive use. So here you can see for once-through systems, withdrawals are high, consumption is low, whereas for recirculating systems, consumption's high, withdrawals are low, and these are for the different fuels that you can see. And so, as we've already discussed right now, that mostly recirculating or dry cooling systems are what is preferred, what is being used predominantly. But you can see that things like nuclear, coal, even solar thermal can have pretty high consumptive use, whereas natural gas, combined cycle, dry-cooled systems, or PV or wind all tend to have very low water use. And fortunately, because of the price of natural gas these days, most of what's being built in the U.S. is the natural gas, PV, and wind. So that alone is beginning to really quickly have an impact on the overall water intensity of our system, and changing the overall water use for thermoelectric power. But we can also take other steps. This is another study that we did with NREL recently, where we, what is the opportunities for really making the entire fleet of power plants use zero fresh water. So the idea is, what are the opportunities for retrofitting existing power plants, either dry cooling, municipal wastewater, or brackish groundwater. So again, zero freshwater withdrawal. So we looked at all over 1,000 water-using power plants in the U.S., and we looked at the cost, the capital, and operating costs to retrofit for each of these 3 options, as well as whether water availability for municipal wastewater or brackish water would be a limiting factor. And so what we found is that basically wastewater, for the most part, was usually the least cost option. Brackish water was usually the next, the dry cooling was the next, but because of limited water availability, the dry cooling tended to get the nod over brackish water. But the real point here is that there's, I think, quite a few opportunities where it might make sense to make these kinds of retrofits, that over half of the power plants could be retrofitted at a cost that's less than 10% of the current wholesale price of electricity produced. And so in other words, about 10% of what it costs to really operate and manage that plant and to cover its overall cost. And so, and more importantly, that many of these plants are in the western United States. These kind of outlined basins are basins where, that were red in that previous, where water stress conditions or limited water availability exists. So you can see a lot of these green areas and light yellow where, the least expensive plants to retrofit are located. So some low-hanging fruit out there potentially to move to our different water use. One of the other pillars, one of the second pillars then is enhancing reliability and resilience of energy and water systems. And so this would be looking at things like integrated modeling and infrastructure risk assessment modeling and putting this information to identify places at risk and improved planning processes. And so this is a big project that myself and a number of other laboratories have been involved with, and what's unique about it is we're bringing capabilities from the national lab, linking that with water managers at the state level from the Western Governors Association, Western States Water Council, and bringing them in contact with the major power planners in the western U.S., WEC and ERCOT. And for those of you not familiar, WEC is this whole area out west, and ERCOT is largely Texas. So these are the groups that operate the grid. And so the idea here was to help them integrate water into their transmission planning. What are the power plants at risk today from water-related issues? And how can we plan the future power plants, where we put the plants, and the new transmission capacities to avoid water-related issues? And so we've done a number of projects. Here's some work that Argonne helped us with. And here was just a quick assessment looking at the major basins in the western U.S. and looking at characteristics of drought, the characteristics of water use, and the kinds of power plants and their water use characteristics. And here you could see some, that probably the greatest risks are in the far northwest or to hydropower, whereas the greatest thermoelectric risks are here in the Texas Gulf Coast because there's still a lot of open loop plants there, and then some here in the lower Colorado. And so with that information, we did a deeper dive here and looking at how both historic droughts and comparing historic droughts to future drought situations and how, which hydropower facilities would be at highest risk. And what we found is the droughts are not too different, but kind of where the drought is most intense varies over these different situations, but ultimately impacts on the hydropower is in line with some of the kinds of droughts, at least out the next 20 years, or kind of in line with the kinds of droughts that we've seen before. But different sets of hydropower facilities are affected in different ways depending on the characteristics of the drought. We've also done some work similarly, again, a lot of work by Argonne looking at how drought might affect thermoelectric power production in the Texas Gulf Coast region. Here, we had a hard time finding a year which was worse than the 2011 drought. So here we found no droughts that had multiple years. And so here we look back at the 55 or the mid-50s drought, but with projected future demands for water and what a drought might look like and which basins are at highest risk, and thus we're able to match that with reservoirs and power plants, and then also do the next step of looking at which ones are most at risk for water being too hot, that the power plants would exceed their thermoelectric, their NPDES thermal limits to operate the power plants. Another thing that we did is kind of forward-looking and then helping them with where they would site their next power plant. And so here we worked with different state water managers in each of the western states to map out water availability. And so we have 5 different sources of water: unappropriated surface and groundwater. This would be fresh surface and groundwater where I could go out and get a water right from the state water engineer. Appropriated water is where I'd have to buy it off a farmer. Municipal wastewater and brackish water, I think, are pretty self-explanatory. Here we map these out. White is an area with really no water availability. The reds and yellows tend to be pretty small amounts of water. You'd have to start really getting into the light greens and so to have enough water to really power a good thermoelectric, say a gas-powered plant. So you can see that, there's not a lot of fresh water available in the West, which is no surprise, but there's a fair amount of wastewater and brackish water, particularly when you start putting it all together. And then against consumptive demands that the state are projecting over the next 20 years. So we're able to take all this information, put it together, and deliver it in particular to WEC. And we also calculated the cost of these waters, recognizing that, things like brackish water and wastewater are going to cost more than the traditional groundwater and appropriated water. So we mapped all this out, and then we gave it, in this case, to WEC, and they used that to constrain where they would site their next power plants. And here we're doing it by Huck 8 Basin, so 1,200 watersheds across the West. The warm colors are where the new demand for water for thermoelectric expansion is positive, where there's new water demands there. The cool colors, the greens and blues, are actually where plants have been displaced, usually coal, and there's now actually more water left over at the end of the day for other uses. The take home, these are 5 different scenarios that, have different assumptions about future demands and other kinds of issues, RPS standards, etc. The takeaway is that largely, again, because of most of the new construction is natural gas, we were able to pretty much spread these demands over the entire West, and only a few basins, these that are outlined, do these new demands exceed 10% of the total water available. Now, in most of these cases, though, they're having to depend on sources beyond fresh water to meet these demands. But also important to note here for these cases, which are assuming pretty stringent emission controls, where a lot of the coal power generation is displaced by natural gas, we end up with a net availability of water in much of the Mountain West. And so, again, very different picture across these different scenarios. And the importance of working, if we work together, we can figure out where to place these power plants so that they have limited impact. Just very quickly, the final strategic pillars. Another one is looking at optimizing energy efficiency for water management, treatment, and distribution. So reducing the amount of energy that goes into moving and treating water, or even extracting energy from our waste streams. Another pillar is increasing safe and productive use of non-traditional water. So for new technologies that would allow us to more inexpensively use produced water, brackish water, wastewater, so improved treatment technologies or integration of technologies. And then the final 2 pillars have to do with making sure we consider the ecosystem impacts of these decisions, so the choices that impact water quality, ecosystem, seismic impacts. And then also the 6th pillar is kind of pulling it all together to looking for the synergies across systems, and very importantly, synergies with other federal agencies. And I think with that, I have tried to give you a really big overview of it all. If you're interested, you can go to this website. This is where all the data is for the projects, and you can also get access to many of the papers that I've been talking about that I've used here. You can also get to the DOE report if you just Google the name of that report. So with that, Manu, I'll turn it back over to you. Thank you very much.
Thanks very much, Vince. That was an outstanding presentation of a rather impressive amount of information related to water and energy. I found it interesting that, compared to the last time I heard you, there's now been even more development in looking at energy plant siting and some impressions there. One of the areas that I find is challenging to get a handle on is groundwater in this context. Did you want to say something about that, particularly in the areas that are currently getting more stressed?
I'm sorry, can you repeat that question again?
Right. With regard to groundwater usage and projections of people looking at how, as a source of water, groundwater may be affected in the different scenarios that you were talking about, is there something you can say?
Well, like I mentioned, Matt, we have an idea of those power plants which are currently using groundwater. For the most part, if the groundwater supplies are at risk, these power plants have, for the most part, the power producers are very aware of these issues and have contingency plans in place. As far as going forward, I think, the example that we did in the West, the importance of really bringing the water managers together with the electric power manager, look at these issues together and to make good choices about where they site power plants. And I think, if we do that together, there are ways of growing without having major impacts on our water system. They are likely, unless new technologies come along, they're going to be a little more costly. But in the long run, to avoid impacts of drought and the uncertainties about operations and even the difficulties of permitting, those costs are probably pretty affordable.
Right. I would like to open it up to people for asking questions. There's a hand sign above your screen that you can, on the fourth item from the top left of your screen, where you can raise a hand to ask questions. So we can go there, but as I'm waiting for people to jump in with questions, Vince, what do you think are the biggest open questions that this research community should be looking at, given the presentation you made?
That's a really good question, and I think the challenge that is there is that, as I mentioned, the regionalization of the energy water problem. That for example, if you consider power plant cooling, that there are very different issues when you look at the East versus the Western United States. In the East, the issues around thermoelectric power plant cooling have more to do with the water quality, the discharge temperatures of the power plants, and in times of drought, they tend to be more limited by the water quality issue, the temperature, the discharge permits, whereas in the West, the bigger concern is more just the physical availability of the water. So, and you find many of these same kinds of issues across all the different energy sectors. So I think at the end of the day, there's not going to be just one solution, nor is there just one problem that really dominates this energy water nexus, but we're going to have to look at many. And what I will say is that we are in the process right now in the national laboratories. We've put together very recently a consortium where we're really focusing on this issue. We're taking this energy water nexus report and trying to distill it down to a program that we can implement that will have high impact over the next 5 to 10 years. And so hopefully in the next 2 to 3 months, we'll really be able to answer that question very specifically for you and say, these are the technology gaps, these are the modeling gaps, these are the policy gaps that really we need to get on top of, and that we can make a big impact over the next 5, 10 years.
Thanks. There's a couple of people with questions, but I don't know how to make them into presenters. So I've just asked the first one to Magdalena to type in her question, and the second one is Abhijit. Maybe he can type in his question also.
So the role of seawater and brackish water desalination and managed aquifers through replenishment and withdrawal as a proactive management strategy. Oh wait, okay, question for speaker, role, okay. So absolutely, I mean certainly seawater is still has a very significant place in the cooling of thermoelectric power plants. I think like on the order of 60 billion gallons per day. And occurring both on the western, eastern coastlines. I think it will continue to have a role, but part of what's changing there is concerns around the environmental issues having to do with open loop cooling. So the impingement and entrainment issues around open loop systems and the impact on the ecosystem because of that. So EPA has moved forward on their 316 rulings that really limit construction of new power plants with those open loop cooling systems. So whether seawater would really be a good alternative going into the future is, I think that will have a pretty major effect on the selection of seawater. Brackish groundwater to date has not been used a lot, but that could certainly be an opportunity and would make sense in a lot of the western states where there's very limited water availability. And that is something, in terms of costs and, trade-offs with other alternatives that are going to have to be taken on a site-by-site basis. Certainly managed groundwater, and you see this in many cases in the West where power plants will have surface water rights, but also have wells to make up water in times of drought. So those are some other options that could be looked at to help manage, issues of both drought and water supply, to meet these demands. So hopefully that answers that question. So yeah. Let's see, do we want to take another one? Presentation. Okay, demand side management in electricity is part of the toolkit to reduce water use and energy. Absolutely, that's certainly going to be, one of the best places. Any savings of any reduction in electricity or energy use is a reduction in water use and vice versa. And so having an impact on the end use of either of those and conserving is certainly a very important part of the puzzle, and it's certainly part of the puzzle that's being looked at as part of the DOE program. I know EPA has, is certainly very high on that. Bureau of Reclamation, their Water Smart program, they have an energy water nexus piece in which they're trying to, look at both opportunities to save water that in turn save energy or vice versa. So, this is definitely a theme that's being adopted by, a broad number of groups. So absolutely. Sorry about that. My screen just went off. Get it back up here. Let's see, what other questions do we have here? How do we drive adoption in industry? Unlike energy and power, industry does not pay the actual real price of water and wastewater treatment technologies produced water at a cost much higher. In this circumstance, how do we drive adoption within industry, incentivize industry? We look at technologies. That's a great question. I'm not sure that I have any real good answers. I think, but part of the solution is going to be, we have to put policies in place, and I think in particular California is one to take a look at. I know that they've put policies in place that require really careful consideration and of using non-traditional waters for power plant cooling, and so either wastewater or brackish groundwater. And basically, you have to really be able to demonstrate, that none of those will meet your needs before you can look at fresh water. So, I mean, that's one case where policies have been set to really force, incentivize industry to make those kinds of decisions. I think the other place, which I know EPA is working hard on, I know it will be a part of this DOE program, and that's simply doing case studies and getting technologies that are emerging but not quite at a commercialization level, getting them out into the hands of folks, doing projects at a pilot level scale, and getting them out there so people can see how they operate. So as far as the real price of water and wastewater, those are continuing to go up, and I think there are other signals in terms of just the values of people conserving water and energy. So I think all of these things are driving. We got to keep making these signals clearer and clearer, though, and what the opportunities and options are. Let's see here, and then other companies like GE, Veolia, et cetera, in good business model. I am probably not the right person to ask on that. I'm familiar with their work. I know that they're engaging. I know they have a very strong business model and are doing some really great things, but I don't know the details there, so I probably shouldn't speak too much on that. Let's see here. I have another question. Did you estimate the cost of purchasing or leasing allocated waters? If so, how? So, yes, we did for the western U.S. What we were assuming, and again, this is based largely on what the states were projecting, is that the states are projecting, and they didn't want to project, any major sell-off of irrigated agriculture, but rather that kind of the natural attrition, if you will, that we've been seeing over the last 20 or 30 years of agriculture to be the kind of course that many of the farmers or agriculture would continue on. And so if we assume that basically that that kind of trend moves forward, then what we did is assume the prices that have been paid for these waters in the past would be a reasonable marker for what they might look like going into the future. And so what we did was we looked at the Water Strategist, which is a report that is put out on an annual basis that records how much, records the price that has been paid for water transfers in the West. And so for that, we had to work at a state level, given the availability of data. And so we looked at that Water Strategist data for water transfers from the ag sector into the municipal or industrial sector, and only for transfers, not for leases. And so that's the data that we used. If you go to that website here, there's a paper that goes over how we came up with all our metrics and costed out all the different water, and it's in environmental research letters. Let's see, yes, I'm happy to share the PDF of the presentation. I don't know how y'all would like to work that, Manu and others. Okay, so yes, you're going to post it on the Columbia Water Center site.
I think we'll have that available. Thanks very much, everyone, for joining, and especially Vince. The main thing I want to say about our project, because we are out of time, is that we are working obviously in cahoots with Vince's group, but one of our goals is to look at actually competition between agriculture, urban, and energy use with respect to water, particularly in the direction of future scenarios and siting, and how these kind of transactions may take place under different regimes and what the economics might be. So the very last question that Adam asked is germane to that issue, especially in light with how drought scenarios with some spatial specificity might map out. So I think we should call this event to a close and thank Vince again. I hear rounds of applause in the background, Vince, as far as electronically possible. And I would encourage everyone who wants to follow up directly with Vince and also with us if they would like to. Thanks.
Thank you.